record.
Okay, this project had its origins about a year ago. I was taking an online course from Springboard called the Foundations of Data Science, and I had to do a capstone project. And I wanted something in the scientific, medical, biological realm, and I ran across the protein database on UCI Berkeley, so I decided to pick that. It seemed like a good fit because proteins are nothing more than biological polymers, and I've been working in the polymer field for most of my career doing polymer synthesis and characterization. So I selected this one. So this is our plan. We're going to start off with some domain knowledge, move on to the data set, exploratory analysis, prediction, and finally results and discussion. Start my timer, okay. Normally I spend quite a bit of time up here because I am talking about protein folding. Most people aren't familiar with that, so it takes a little bit of explanation. It's not as intuitive as something like a click-through rate or profit and loss or that type of thing. So we're going to spend minimal time on that because of the time constraints, just enough so that you get a rough idea of what we're measuring. And we'll spend most of the time here on the exploratory analysis for a couple of reasons. But basically, it's my opinion that people don't spend enough time there. They kind of look at the data and move right on to prediction. Okay, the variable we're going to predict is this one right here, RMSD. And I'll give you an explanation of that in a minute. That is the root mean squared deviation. If you spend any time in the laboratory, physics lab or chemistry lab, something like that, you're probably familiar with that. And again, I'll explain a little later. And what it is a measurement that we use to make a simple quantitative single point comparison between two protein structures. They can either be the structures of two different proteins, which is going to be the case here, or maybe how the protein changes over time. We collect the data using the methods of combinatorial chemistry, which is a whole bunch of methods and procedures to collect, store, and analyze very, very large amounts of data. It is relatively recent. It's only come into the fore in the last maybe 25, 30 years or so. It has both academic and commercial applications. Drug companies are really hot on these methods. And here's the big point here. None of this would be possible without the big data methodology to collect, store, and analyze huge volumes of data. So this is a pictorial representation of what that combinatorial chemistry process looks like. You can have 20 or 30 steps. It's all highly automated, it's highly data intensive, and robotics play a big part in this. Now, as I mentioned, proteins are polymers. They are a specific sequence of amino acids, and they undergo intramolecular and intermolecular interactions to form 3D structures. And its 3D structures is really important in proteins, because that's what gives it the biological activity. You mess up the 3D structure, it doesn't work like it's supposed to. We talk about denaturing. So there's primary, secondary, tertiary, which is what we are interested in quaternary. I won't explain all of these in any sort of detail, but primary is the specific sequence of amino acids from the head to the tail. Secondary structure right here, that would be how they arrange themselves in space locally. A sequence of maybe 15 or 20 of the monomeric amino acid units will form sheets or spirals depending on their structure. And then finally, almost finally rather, we get down here to the tertiary structure. They fold themselves into complex three-dimensional shapes, and they can agglomerate those tertiary structures, can agglomerate to form quaternary structures. And here's the depiction of it. We have the primary structure here, the amino acids along the chain. This is the case of spiral. And over here's the tertiary structure. You can see how it's all folded, and then the quaternary structure. Everybody with me? I'm kind of racing through this so we can get to the interesting part. So that's what we're trying to predict, the RMSD. And what it is, it's just a total of the distance between corresponding atoms on two chains. So we have the blue chain and the green chain. And we look at the location of the first alpha carbon atom, one chain on the blue chain, and we look at the location of the corresponding atom on the green chain, measure the distance, okay, divide by n and all that sort of thing. So that gives us what the average distance is. And the thinking here is these are highly complex shapes. We want to describe them, but we'd like to do it simply. And this gives us a single measure. And again, behind it, the smaller the RMSD, again, which is what we want to predict, the more similar they are in structure. And an example of that would be if you isolate a protein and you don't know its function, you have an idea of its structure, you can compare it to another protein in huge protein databases and maybe get some idea of what its function is. Everybody okay with that? So it has some real world relevance. For example, sickle cell anemia takes place when a genetic defect substitutes valine for glutamic acid in this chain here. And it messes up the protein folding royally and it doesn't have the same structure. One genetic defect replaces every glutamic acid with the valine. This is going to be very hydrophilic, so it would want to be on the outside of the shape. Whereas this isopropyl group here on the valine is hydrophobic, so it would want to be inside, folded up, because it doesn't like to be in water. It's an organic. Okay, and here's where I got the data from the critical assessment of protein structure prediction, and one of the people there who engaged in that sort of thing posted it at the Irvine Data Repository in that CASP 59. Every other year, people who study these sorts of things get together and they have themselves some sort of academic convention, and they have contests to predict protein structure every other year, and that's what they do. And there's huge protein databases out there with specialized analytic tools embedded within the databases to help people measure these things. And finally, here is the data set. Okay, good. Go back here. It's clean and tidy. We won't go into detail on that. Consult Hadley Wickham if you want to know about clean and tidy. And what we're looking at is 9 factors, 9 measurements that we want to use as predictors of the RMSD so that we don't have to go through that whole complicated analysis and synthesis and analysis of the protein. That was that picture I flashed up. It's all the highly automated chemistry stuff. And notice one thing here. Surface area, nonpolar exposed surface area, fractional area of exposed nonpolar residue. They're all some function of the surface area. So we think, could there be some correlation here? So take a look at it. Oh, by the way, here's the size of the data set. I think 43,300 and some. Deep but not very wide by a lot of standards, especially marketing standards. So first thing, let's take a look at the data. This is just a lattice plot, and I took a sample of 1,000 points because if I put 47,000 here, I couldn't see anything. So this is a random sample, and let's note a couple of things about this. First of all, RMSD and all these predictor variables here. This is the upper left-hand corner. I just plotted 5 of them to make it easy to see. Look at that distribution. It's weird. It's like a bifurcated distribution. So that tells us it's not going to be easy to model because it looks like there's 2 separate groups there. The other thing we want to notice is 45-degree straight lines here and there. Everybody know what we're looking at here with the lattice plot? Good. I'll just race right through that then. And we have a lot of correlations. Well, look at all that, especially here. This is F1 and F5 highly correlated. Oh, look at this one, F5, and it's F1 again. How about F2 and F1? It's a little more spread, but it's still highly correlated. So that's a no-no if you want to do anything like a linear regression or any other model. Everybody okay? Questions?
You're trying to
go back?
RMSD is a target variable.
That's the target variable. That's what we want to predict.
How do you choose when you calculate RMSD, you have to take one protein and you compare it with the other, right?
We compare corresponding alpha atoms on the backbone, not carbon atoms. Alpha atoms, that's the optically active carbon atom on the protein chain. Okay? That's getting a little heavy chemistry here, but that's how we do it. See me afterwards. I'll be happy to talk to you about it.
Is it a univariate correlation?
Univariate?
All of these, F1, F2, F5, the correlations?
There are two-factor interactions.
Scatter plots.
It's a scatter plot, yeah.
No, I'm talking the F1 to F5, those different.
Each one of those are univariate.
Each one of those are the univariate correlations.
Yeah.
Yes.
Okay.
Yes. Two factors. This would be the x-axis, x5, and then you come up here on the y-axis. It's all two factors. Okay. Have to race through this. Next thing I did was find correlation coefficients. I hope everybody knows what that is. Okay, look at some of these correlations here. They're 0.94, 0.91. So we've got a problem there. And again, I just took the core function from the base R package. And now we go up here again in exploratory analysis. RMSD, total surface area. This was F1. This is just the first scatter plot, and I enlarged it. And I'm not going to do that for all of them because they're all pretty much the same. So you see you have one relationship here and another relationship here.
Do you see this with any random sample?
Yes. Next thing I did was look at the descriptive statistics. I think this is very important because if your data doesn't fit all the assumptions, then your analysis is going to be off. And the way I did that, I used the described function from the site package. Anybody use the site package?
Yeah.
It was developed for psychometrics, but I use it for almost everything. I think it's really good. It gives you what you need and more. So I ran the select function from dplyr to select what I wanted, and we get these values across the top. Everybody know kurtosis? That's how pointed and narrow the distribution is. And we see we got a problem here. We've got a skew which is about 20 times higher than the skews of the other factor, and kurtosis is astronomical. There's something awful wrong here. A highly localized and pointed kurtosis would be about 6 or 8, and we're at 804. And we move on. And that was the Euclidean distance. The other thing I didn't mention about this data set, there's no data dictionary, no explanation of what the variables were. The guy just threw it up there and that's it. So we're not sure what it is, but let's take a quick look at it. This is the data set, all 47,000. And it's hard to see, but this is percent of total. This is just a histogram. And this is F7 along here. And through that long axis, there's something going on. So once again, we take our sample and plot that. It's the same data, and we see that, yes, it is pointed. Here we have some outliers. Overall, it's a small proportion of all the data. So for now, we'll just ignore it, but there's another reason we're going to ignore it. There's table factors. We'll skip that. RMSD and F7, zero correlation. So we'll just ignore that part right there. And now we start building our models. I just built 8 linear models here. And there's a lot of art in this sort of thing, especially when you talk about methodology, where you're going to start, which direction you're going to go. So I started with a linear model just using the LM function in base R. Started with F3. because that had the highest correlation with the RMSD. It's one of the things we found from our scatter plot, from our correlation matrix. And I kept adding terms till looks like I maxed out at about 0.26, added some other terms here for nonlinear type things. And I also added an interaction term there. Whenever you see something split like that or two separate groups, that's an indication that you may have a two-factor interaction. Everybody know what a two-factor interaction is? No? Yes? Okay, most people are shaking their head yes. For those who don't want to shake their heads, no, it's when the effect of one variable on your predictor varies depending upon the setting of another variable. Okay, so results and discussion. We can skip the finer points up here and skip down to here. Evaluation of results depends on content. When I was working on this project, I had an advisor at Springboard. His name was Matthew Kent, and he was working at Sloan Kettering at the time. I don't know if he's still there, but at the time he was just there. And I said, oh man, I wish we would have picked a different data set, different project. Did all this work on it, and I only got 0.26. Now, at the time, I came out of the lab, so I'm used to getting correlation coefficients like 0.92, 0.96, something like that, especially when trying to find a proxy variable. So I thought that was low, and he said, no, that's pretty good. He said, we just had a group finish up a project here. They worked on a protein structure for a week, and they only got 0.11, and everybody was happy with that. So you have to bring some perspective to this, and also a little bit of judgment. You can't get data out of a data set if the data isn't in that data set. So you don't want to overanalyze it. You move on to something else. I came out of industrial environment. People are always in a hurry. So move on to something else. We got what we could out of this one. And let's see, I did a whole bunch more work, but don't have time to talk about it. We'll skip through that, and I'll leave you.
Hey, Stan, can I ask you a quick question? Yes. A couple places you labeled something a lattice plot.
Yes.
Now, lattice is a package in R, I think.
Well, it is a package in R, but I just used the plot package here.
But I'm curious, is that a generic term for a type of plot?
Yeah.
Okay, because and it's the type of plot that you had up earlier. Okay,
right.
Had a whole bunch of scatter plots. Okay.
It's known as the lattice plot. And we had statistical results. There's statistical results. That was our R squared. And we had practical results, okay? Which, considering our system, biological system, highly complex, don't know too much about what we're looking at, and also our data set wasn't very wide. We only had nine variables, and most of them are correlated with something else. So it's okay. And this is all posted. All the R code is posted on GitHub, and there's a longer version of this presentation on YouTube. I gave a webinar for it, and the good folks at Springboard were kind enough to post it for me. And there it is. Feel free to use any of this stuff. It's Creative Commons license, share and share alike, nonprofit with attribution. And I leave you with these words of wisdom from XKCD, one of my favorite all-time websites. It says, don't trust a linear regression when it's harder to guess the direction of the correlation from the scatter plot than to find a new constellation on it. And here he did a whole lot of analysis and came up with Rex Thor the dog bearer. So the moral of the story is that know when to quit, don't try to find something that's not there. That's it. And all this is available.